Okay, so as people file back in for the second part of the session, again, I'm Yoni Brandy. I'm a second year at the University of Kansas, and I'll be moderating this. So Konstantin, if you are ready, can you start sharing your slides?
I can't, yeah, I need to. So okay. I'm not sure what you're seeing.
I can see your slide deck. So
perfect.
And just a heads up, I'll be notifying everybody at 2 minutes, unless you're giving a dissertation talk, in which case I'll do 5 and 2. Okay.
So hi everybody. I'm Konstantin from the University of Kiel, where I most recently became a private docent. And I want to thank Yoni for the introduction, and thanks to the organizers for giving me the opportunity to present one of our most recent DFG-funded projects, which is in collaboration with Lee Grenfell from DLR Berlin and Miriam Sindhuber from the Karlsruhe Institute of Technology in Germany. Now, studying the impact of cosmic rays on exoplanetary atmospheres is a rather fast and newly emerging field, which we, for example, started in 2017. And INCREASE, in particular, will build on the experience we gained over the past years with the main objective of further understanding the atmospheres of rocky exoplanets, exomoons, as well as mini-gas planets, using this model suite that I will briefly describe today. Now, the most puzzling questions for us are what processes determine whether these worlds retain their atmospheres, how do different atmospheres evolve in these systems over time, and how do our results actually compare with observations, for example, of the James Webb Space Telescope in the near future. Now, our main focus, of course, is on cosmic rays, and we have two categories like galactic cosmic rays. And as you can see, they are originating far outside the stellar system. So they are produced or accelerated in supernova remnants and their shock fronts. So they reach really high energies, whereas the stellar cosmic rays are accelerated at the star itself. So in stellar flares or the accompanying coronal mass ejections, and thus reaching only less energy. So in the giga-electron volt regime. Now, since stars have a magnetic field, and the magnetic field is frozen into the stellar wind, and this is carried outwards, like an astrosphere is being built up, like you know, from the heliosphere. And so this astrosphere is protecting the stellar environment and thus potentially habitable planets against the isotropically incoming galactic cosmic rays. And the transport of cosmic rays within is described by Parker's transport equation given here, which you can either solve analytically, as it is done in the exoplanetary context so far, or numerically, for example, with the help of stochastic differential equations. So the results are shown here in this middle panel. So we have the energy of the particle, we have the differential intensity. Black is what is coming from the outside into your astrosphere. And in purple is the spectra that we know from Earth. So quite demodulation in the low energy part. And in blue, you see results for LHS 1140, which is a quiet, cool star, so an M star. And if you use the analytic solutions, as for example, presented in Lee Rogers et al. 2021, you end up with the fact that galactic cosmic rays do not play a critical role when it comes to habitability. However, if you use this numerical solutions, as we did in one of our last studies, you see that the modulation might be much lesser than previously thought. So in an astrosphere, like in the case of LHS 1140b, which is really small compared to the heliosphere or Proxima Centauri, you would end up with much more galactic cosmic rays than previously thought. So 3D MHD astrospheric and transport modeling might be necessary to get an idea what is really going on here. Now, when it comes to the stellar particles, it gets even more frustrating, I would say, because there is this focused transport along the magnetic field lines, which is usually described by the Roloff equation. However, the problem is that you have information, you're missing the information on the injection profile. And this will not be measured in the meantime in the next few years, or at all in the case of stars. So we have to rely on other known solar relations, for example, the peak size distribution, so the relation between the X-ray flare intensity, which we can measure from other stars, and the peak proton flux that you can measure with GOES, for example, around the Earth. And then you put all of this into one diagram, and you can assume a power law distribution, which then can be extrapolated to the cool star regime of X-ray flares in order to get an idea about the proton flux. And that these charged particles have an impact on the atmospheres can be seen in our solar system. So we see here the impact in case of the ion pair production rate. So particles come in and they interact with your atmosphere and produce secondary particles, for example, ions. And this is shown here. So we have in blue the Earth, so an N2O2 dominated atmosphere, and then two CO2 dominated atmospheres, Venus here in orange, and red is Mars. And what you see is that galactic cosmic rays already do play a role when it comes to terrestrial planets here in our solar system. However, strong energetic particle events have a much stronger impact on the ionization rates, and this ionization rate is directly correlated with the chemistry of the atmosphere, and this is shown here by the ozone changes measured with Envisat MIPAS due to a strong energetic particle event. So it's fair to say that space weather has a direct influence on the atmosphere and the chemistry, and therefore, of course, on the biosignatures and the habitability. So in our model suite increase, we gather knowledge about the stellar particle spectra. We have a code that is taking care of the interaction inside the planetary magnetic field. We developed a new atmospheric code to model these secondary particles, to model the ionization rates and the dose rates. And we couple all of this with a chemistry climate model, the Terra model, as well as an ion chemistry model, which is known as Exotic. And with all of that, we are not only able to give an idea or get an idea about the dose rates, but also the UVB and UVC flux at the top of the, or at the bottom of the planet, but also, and this is most importantly, about the chemical analysis of biosignatures, as we will hopefully see in the future with James Webb. So a particular interesting application was to study the impact of the harsh radiation environment of cool stars on Earth-like exoplanets, as is shown here in two studies we published in the 2 years. And the key finding is that these works, is that the relatively easy to detect biosignature ozone is likely depleted in these Earth-like atmospheres due to the activity of the star. However, we were also able to see a strong increase in the biosignature HNO3, which might be a direct indicator for stellar activity. And with that, I'm almost finished. So in the near future, we are focusing also on CO2-dominated atmospheres, on steam atmospheres, in order to tackle all of these three questions. We are now performing evolutionary snapshots, so changing the cosmic ray flux over time, and we hopefully will be able to have a look at spectroscopic outputs in the near future. So I'm at the end, and thank you for your attention, and I'm open for a quick question, I guess.
Yeah, thank you, Konstantin. Sorry, I forgot to actually introduce Konstantin first. Again, he's a postdoc at Kiel, presenting one of the greater acronyms I've seen this year. Just to do a quick question, here's one from Seth Redfield. Great talk, Konstantin. I was wondering what your thoughts were on the changes in the heliosphere in time as the sun traverses different ISM environments. It could be at key times in the history of the Earth that the galactic cosmic ray flux was quite different than today.
Yes. So the short answer is yes, they're. So first of all, you see the changes already within the solar activity cycle. So it's like the heliosphere is breathing within this 22-year cycles. So there is already the change, but then there was also passing of spiral arms of our galaxy, and there you have denser regions, and then you have regions with much more material, much more stars, much more, let's say, supernova remnants, and then you increase the galactic cosmic ray flux. So this is something we also have to address when it comes to exoplanets.
Hey,
sorry.
And And if Lindsey could start her video and prepare a slide, we have about 30 seconds for possibly Howard's question. I see your atmosphere altitude, actually, that one should probably get handled offline. So Konstantin, thanks again for your really great talk.
Thank
you. We can move on. So next up is Lindsey Weiser, who is a second year at Arizona State, presenting some self-consistent constraints for a population of 20 hot Jupiter emission spectra.
All right, can everyone hear me? Looks like it. Okay. So yeah, hi, I'm Lindsey Weiser. Like you said, I'm a second year PhD student at ASU, working with Dr. Michael Line. And I'll be presenting results from a self-consistent one-dimensional atmosphere models for a population of hot Jupiter emission spectra. So I had three core questions motivating this work. First, what does heat redistribution say about the climates of these planets? General circulation models, or GCMs, as I'll call them, have made predictions for day-night temperature contrasts with and without clouds, so we compare results to those trends. Second, do atmospheric compositions agree with planetary formation theories? So hints at a planet's formation history, including where it formed and how it may be encoded in the atmosphere, or how it formed and where may be encoded in the atmosphere. So I look at metallicities and C to O ratios to start thinking about those questions. And third, how well do these models fit the data? So data comes from a uniform reduction of Hubble with C3 points, with additional 1 or 2 Spitzer points for many of the planets. And following this uniform reduction and modeling process, enables us to make some useful comparisons between these planets. So here's just a fun figure showing spectrum fits to 12 of the planets in this population, giving a rough idea of distribution. You can see the Hubble with C3 points and the additional Spitzer points over there on the right. Looking at heat redistribution first, colors of the points are going to correlate with the chi-squareds of the model data fits. So we'll think more about those later, but the heat redistribution parameter is essentially a measure of how much circulation is occurring. So a value of 1 would mean full redistribution, 2 would mean only on the day side, and 2.6, which is the maximum, would be there's no heat transport happening. So we plot predictions from GCMs, and essentially when there are no night side clouds, heat redistribution is relatively efficient. But the presence of clouds makes this tougher because it's harder for heat to escape to the night side. So our results do roughly follow the upward trend as evidenced by positive correlation values. And they do seem more consistent with the presence of night side clouds as we'd expect for these planets. Metallicity proves a little harder to constrain. Looking at our determinations, there isn't much of a trend. However, I do plot trends from other published work. Some of these are based on solar system observations, while others take into account transmission spectroscopy results from exoplanets. But with exoplanets, the trend is not very clear, and we're not alone in finding this. So for now, metallicity trends remain in question, but this is an interesting thing to continue thinking about, especially as we have more planets in these evaluations. Looking at carbon to oxygen ratios, C to O ratios have been linked to planetary formation because beyond various ice lines in a protoplanetary disk, so where some species condense out, you'll get different ratios of carbon and oxygen in different phases. So in the potential giant planet forming region, which would be beyond the H2O line, we expect more oxygen locked in ice with carbon as a gas. So from core accretion models, we'd expect many of our planets to have C to O ratios around solar, which we have marked on this plot. And a number of the planets do hover around there. A lower C to O then could correlate with more planetesimal dominated formation with oxygen-rich solids polluting the atmosphere later on, While a higher value greater than 0 for log C to O is pretty unexpected and may require some more complicated formation pathways. So while we haven't achieved tight constraints on all of these planets, we do find upper limits on many of them which agree with lower values. So taking a step back and looking at the modeling process, assumptions make a big difference. So classic 1D retrievals are going to be computationally efficient, but part of that trade-off is that they make minimal assumptions or more minimal assumptions about the necessary physics. And this can be great because it can provide flexible fits that could illuminate surprising results that could be disfavored by more restrictive models. But the downside is that they also may be non-physical. And on the other side of the spectrum, there are GCMs, which are computationally intensive and include more couplings to produce a robust 3D model. But these are difficult to do on the large scale within a reasonable time frame. So what we do is produce these 1D self-consistent forward grid models. The self-consistency means we add additional couplings to mitigate the possibility for unphysical solutions, while also keeping the model simple enough that we can run them on a large scale since they're 1D. And we make grids, meaning we make a bunch of models with different parameters, and then we use Bayesian statistical methods to select the best fit. So the last question I mentioned in the beginning was how good are the model fits? And the answer is really good in many of the cases. So for each planet, we ran 5 different cases, fixing various parameters. So fixing to solar composition or cloudy night side values. And for the most part, we found really low chi-squared values. Some of them are less low. That could be a result of data issues. It could also be a result, or it could also be illuminating variability in the population. So that's also interesting to look at. And with that, I'll just leave my takeaways up, and I'm happy to take questions in the last couple minutes.
Thanks, Lindsey, for a really great talk. Any audience questions? If there aren't any, I'll take moderator's prerogative. This is a really interesting combination for GCMs and those sort of traditional 1D retrievals that I think we're used to. How extensible do you think this is to different populations and other potential things that we should be looking at with James Webb?
Yeah, so here I'm focusing on hot and ultra hot Jupiters, but this is definitely can be extended to different populations, perhaps adding or adjusting molecular species present in the models. But yes, I think this is definitely extendable to other populations. And I am hoping to apply it to James Webb data later on.
And we have a question from Peter Gall. Great talk. Are the less than 1 reduced chi-squares an issue?
So in many of the cases, because the models are already pretty restrictive to being, because they're self-consistent and they're kind of restricting to equilibrium, I'm not particularly worried about those, but it's definitely something to note. But yeah, no, I'm not especially worried about them.
Okay. Sounds good. We have one from Ted Kamachek. Great talk. I really like this framework. Are you planning on doing a combined analysis, including low and high resolution data sets, especially for metallicity and C to O ratio?
So our group does both high and low res, so that's definitely something we could consider doing. It's not my immediate plan, but yeah, that's definitely something we should consider doing since we have the expertise for both in our group.
Okay. And with that, I think we should probably move on to Peter if he can prepare his slides. Any other further questions can be handled offline or in the Slack as usual. So next up is Peter Gown, who's a staff scientist at Carnegie, presenting a universal cloud composition on the night sides of hot Jupiters. And Peter, I'll send you a message at your warning times.
Great. Thank you, Yoni, for that introduction, and thank you to the CHAMPS collaboration for putting this together. Y'all are champs for doing this. So today, I'm really happy to tell you about clouds on the night sides of hot Jupiters, as Lindsey just mentioned. So the motivation for this study are the recent observations showing the day side and night side temperatures of a collection of hot Jupiters. So these observations show that while the day side gets hotter and hotter and hotter with increasing equilibrium temperature, perhaps as expected, the night side stays a cool 1100 Kelvin throughout this entire equilibrium temperature range, all the way up to 2500 Kelvin. So models have tried to explain this, and the explanation is likely a combination of dynamics and clouds. So dynamics are important because it controls how much heat gets transported to the night side from the day side. And one way to explain the near constant night side temperature is that as the day side gets hotter, the radiative time scale goes down, and so relatively less heat gets transported to the night side. And so the night side probably should get hotter slower than the day side. However, it's hard for some of these models to explain why the night side is both constant in temperature, but also such low temperatures as well, 1100 Kelvin, throughout this entire range. And so that's where clouds can come in. So one way clouds can produce both a constant night side temperature trend and the low temperatures is by tying the observed temperature to the condensation temperature of the clouds. So here's a very simple toy model showing a cool planet in the with the blue temperature pressure profile, a hotter planet in the orange profile, and the condensation curve of some cloud species put here in comparison. So just as a guide, where the condensation curve and the TB profiles intersect is where you have a cloud forming. This is where the cloud base forms. And so if you have a cloud forming on the cold planet and you probe the cloud top, then you will observe this temperature, whatever it is. If you go to the hotter planet, however, you end up still observing about the same temperature because the cloud would have moved up to where it can condense out. And so in this way, you can get this constant night side temperature through observations. So this is all nice and good, but equilibrium condensation models predict that there are lots of different clouds, not just one magic cloud. Here I show a compilation of condensation curves for both solar system planets and hotter exoplanets compared to TB profiles of a couple of planets that we're familiar with. And one thing to note, particularly for the hot Jupiter temperature regime, there are lots and lots of predicted cloud species. So how do you get this constant night side cloud? Well, so we looked into this 2 years ago by modeling these clouds using a kinetic model of cloud formation. So here we take into account the rates at which clouds actually form by taking into account their material properties. And we found that, in fact, even though these models predict a lot of different cloud species, only one dominates over all of them throughout this temperature range. What we found in terms of fractional contribution to cloud opacity as a function of equilibrium temperature is that silicate clouds essentially is the dominant magic cloud that could exist and dominate over others on all these hot Jupiters. And so when we got this result and we saw the data, we thought, okay, well, let's see if this works to explain the night side temperatures. And by we, I mean myself and Dinah Powell, currently a Sagnick Fellow at Harvard. And so together we looked into, we used TB profiles from GCMs, and we modeled these clouds using these TB profiles. And perhaps not surprisingly, same model, right? We got that silicate clouds dominated over all the other cloud species. And when we compared our computed brightness temperatures to the to the data, we found that we are able to get this flat and sometimes even slightly downward trend in the night side temperature as a function of equilibrium temperature. So here I show the results for the 3.6, 4.5 micron Spitzer bands. The blue curves are the night side models, And if you didn't have clouds, as I said earlier, dynamics will keep the night side temperature still not too hot, but there is still an upward trend. Whereas with the clouds, you can get a flat, almost downward trend. Now that said, there's a lot of scatter in the data. The error bars are also quite large. And so we look forward to future observations with JWST, for example, that can constrain this a little bit more. So one more prediction of this model is that because the night side is covered in silicate clouds, you could look for silicate absorption features. And so some of us might be familiar with the silicate feature in transmission, where you see a bump at 10 microns. Well, here in emission, because of absorption, there is a dip. And we predict that some of these signals could have amplitudes of 100 ppm or more, which may be on the edge of observation by JWST. I'd like to end not with really a conclusion, but with an interesting implication, which is that at some point, the night side clouds will run out. As you push the cloud base up and up, higher and higher up, you're going to run out of material to make optically thick clouds. So at that point, which we think that transition probably occurs between 2000 and 3000 Kelvin, the radiative balance of the planet will change considerably, because suddenly you don't have a night side cloud blanket that's stopping all emission from the night side. You can now emit from the night side again. So that should change the radiative balance of temperature structure. That should change the dynamics, and that should definitely change the night side spectrum. So this will be something interesting to look at by observing a population of hot Jupiters, their phase curves for this temperature range. So something for cycle 2 perhaps. So with that, I'd like to thank you for your time and take your questions and comments. Thank you.
Thanks, Peter, for a really great talk. Any audience questions here? One from Sean Dongle Goldman. Peter, how do you think photochemical aerosols, perhaps blown over from the day side, could impact your top-level conclusions?
That's a great question. Yeah, so we did not include hazes in here, or photochemical aerosols, just as a simplification. But it really comes down to their production rate and therefore their optical depth. Since we're seeing everything in nadir geometry, this is emission. And so it is possible if the hazes are not too optically thick, we can see right through them. On the other hand, the hazes could heat the atmosphere, causing inversions. And so that would muck up the picture some more. But definitely something to consider in the future. Yeah.
Okay, and there's another one from Vivian Parmentier. When do you think the night side clouds dissipate? If the radiative argument makes the night side cool, it should stay cloudy for even high equilibrium temperature.
Right. And so this is where a couple model will be nice to have. And so the TP profiles I showed earlier, which is from Vivian's model, show that, oh, sorry, I did not show that. That was in my backup slides. So I'll show my backup slides then. Somewhere. No, wait, what am I saying? I did not, sorry, COVID brain. There we go. So the night side, even though it increases in temperature much slower, it does increase in temperature. And so, right, and so at some point, the TP profile will reach a point where the available cloud materials run out. I'm not sure where that is. I would love to figure that out through observations. But also at the same time, you have other heating sources coming up for the ultra hots, like H2 recombination heating, for example. And so that would also accelerate sort of the boiling off of night side clouds. But where exactly, I don't know. How gradual is that transition? I don't know, but it's something interesting to observe.
Okay, and possibly last question here from Mark Elowitz. Did you try modeling the transition zone between the day and night side regions?
I did not, but I point you to Powell et al. 2019 for exactly that. And so, she did a great job looking at inhomogeneities in the limb clouds. And, there's some interest. It's a very big paper. So there's a lot of details in there. And I'll point you to check that out.
Okay. If there are no other questions, I think we can probably move on to our next speaker.
Thank you.
Thanks, Peter, again. Our next speaker is Megan Mansfield, who is a Sagan Fellow at the University of Arizona Stewart Observatory, and she'll be presenting first results from a high-resolution transit survey with Gemini South IGRINS. And again, I'll send you a message at your 2-minute warning.
Awesome. Thanks for the introduction. As Yoni said, I'm going to be sharing some first results on an initial metallicity measurement for a planet that's part of this large survey that we're doing with Gemini South, and then I'll talk a little more about the bigger hopes for this survey. This was a transit observation of WASP-76b, which is an ultra-hot Jupiter, and we were looking at this planet with the IGRIN spectrograph, which is on Gemini South, as I said. It's got a resolution of about 45,000, and it covers a wavelength range spanning from about 1.5 to 2.5 microns. So within this wavelength range, it covers features of all of the major primary carbon and oxygen-bearing species that we expect to exist in hot Jupiters, such as water, carbon monoxide, things like that. So the primary goal of these observations was to detect those species and use that to constrain the metallicity and C/O ratio of WASP-76b. So we observed a single transit last October. Here I'm just showing in this left-hand figure the signal to noise for each of the orders of one of our exposures. We achieved a signal to noise of about 200 per AB pair for each of these exposures. And then on the right-hand side, I'm showing we used a principal component analysis, which Peter gave you guys a great introduction to earlier, which is awesome, so I don't have to make all of those animations that he showed you all earlier. But we used that to separate the signal of the planet out from the signal of the star, and as well as telluric features. So then we did a cross correlation with a model template to detect the atmosphere of WASP-76b. So here, this is just overall detecting the atmosphere, not focused on an individual molecule. And in this plot here, I'm showing the cross correlation over the phases we observed in this transit as a function of radial velocity. And you can see two features pop out of here. First, whoops. There we go. The one I've highlighted in red here on the diagonal, that's the signal from the planet itself. And then this blue one that's more straight up and down is the signal from the star WASP-76 over that transit. So then if we sum up all of this signal into a single cross correlation as a function of the systemic velocity and the planet's Keplerian velocity, we get overall about an 18 sigma detection of the atmosphere of WASP-76b. And we see this detection at pretty similar Kp and Vcis values to what were previously published in the literature, which is indicated by these white lines here. So now is the part where, unfortunately, we don't have finalized constraints yet, but we've just started looking at doing a retrieval on these data to get the actual atmospheric composition of WASP-76b from here. So what I'm showing here are just a simple pairs plot from an initial retrieval that we did, where we were fitting for only the biggest things we thought would be able to pop out of this data, water, carbon monoxide, H-, and then we also fit for some clouds. So we were able to detect water and carbon monoxide at a pretty high significance in these data. If you go based on just these constraints, that would suggest that we're seeing a substellar metallicity and a superstellar C/O for this planet. But there's a lot of caveats in that. For example, there's a lot of other molecules that are likely to appear on this planet, such as FEH, which has been detected on hot Jupiters before. And there's also some processes that might be influencing these abundances, such as water dissociation, which is expected to occur on WASP-76b. So going forward, we're going to be doing a lot more retrievals with different molecules like FEH and OH, which is a product of that water dissociation, in order to try and get a better overall idea of the composition of WASP-76b's atmosphere. So as I said at the beginning, this is the first observations from a high-resolution transit survey that's going to be measuring the transmission spectra of 11 different exoplanets with the IGRIN spectrograph. These planets, which I'm showing here on the right, span a range of different masses and equilibrium temperatures. And as I said at the beginning, IGRINS covers all of the features of primary carbon and oxygen bearing molecules that we expect to be in the atmospheres of these planets. So we're going to use this survey to look for trends in those abundances with mass and temperature, as well as the age of these planets. And then we're also hoping to combine this data set with other data sets. Several of these planets have Hubble and Spitzer data existing. A lot of them have planned JWST cycle 1 observations. And also a lot of these planets have published high resolution data at optical wavelengths with other planets, with other instruments. So we're going to use all of those data sets combined to get a much fuller picture of the atmospheric abundances of these planets. So before I end, I just want to acknowledge a few people, all of the co-Is of this program, in particular Michael Line, who has been patiently trying to teach an observer how to do an atmospheric retrieval. Also the Gemini South and IGRINS science support staff, who have been really helpful in figuring out how to use this awesome instrument for exoplanet science. I want to acknowledge the NASA Hubble Fellowship Program for the funding that makes it possible for me to be doing this work, and also everyone at CHAMPS for putting together this seminar. It's been really great seeing what everyone's been doing the past year, and I'm looking forward to the rest of the talks later today. So just to conclude, we've detected the atmosphere of WASP-76b in a single transit with the IGRINS spectrograph and put initial constraints on the water and CO abundances in its atmosphere. We're going to be doing ongoing work to look for other molecules that might exist in this planet's atmosphere and get a better constraint on its metallicity and C/O ratio. We also might be doing some work in the future to look for differences between the morning and evening terminators in our data, because that's something that's been observed on WASP-76 in several other papers recently. And these are just the first results from an upcoming survey of 11 transiting planets with the IGRINS spectrograph. So look for more results from that survey over the next couple of years. Thanks again, and I'd be happy to take any questions.
Thank you, Megan, for a really great talk. Any audience questions? Maybe I'll just start off by asking whether there are any sort of initial things you've noticed by comparing these planets to archival Hubble and Spitzer observations.
Yeah, so I haven't really looked in detail at comparing this planet to the Hubble and Spitzer observations yet. I guess a little bit earlier in Peter's talk, he talked about comparing some data that we had for WASP-77, although that was secondary eclipse emission spectra, and this is for transmission. But it looked like, at least from that comparison for the emission data for WASP-77, those were looking pretty, like they produced pretty similar spectra, the high resolution and low resolution results. So that's pretty good. That's pretty comforting, because it's nice to have these two really different data analysis methods that give us pretty similar results. But yeah, I'm looking forward to extending that to the planets in this survey as well.
Cool. Very exciting. Any other audience questions? One from Eliza Kempton. Thanks, Megan. Do you have high enough signal to noise to time resolve the transit in your retrievals?
Yeah, that is a good question. So I guess it depends on exactly what you want to achieve with that, with like what signal to noise, like what you need to get what you're looking for in that. At least for, if we're talking about looking at differences between the morning and evening terminators here, I don't think like we have high enough signal to noise to do like different results for individual exposures or anything like that, but we might be able to do something like first half of the transit detections versus second half of the transit detections, or, you know, like the little bit in ingress versus little bit in egress, comparing, like summing up those. So they would definitely be lower signal to noise detections, but I still think it would be interesting to look for those differences, especially because WASP-76 has had so many results recently for differences in composition between the terminators. Yeah.
Any other audience questions? We still have about a minute. If not, then I guess we can thank Megan again and get started for our next speaker. So Sagnick Mukherjee is the second year at UCSC, and he'll be presenting some results probing vertical mixing in substellar atmospheres with radiative convective disequilibrium models. And Sagnick, again, I will message you at 2 minutes.
Yeah, thanks. Thanks, Yanni, for the introduction. So yeah, hello, you all. I'm going to present on probing atmospheric physics with disequilibrium chemistry in brown dwarfs mainly. So let me begin by explaining what do I mean by disequilibrium chemistry. So if you look at the typical model of a brown dwarf atmosphere and the temperature pressure profile, the upper part of the atmosphere is typically radiative in nature, where majority of the energy is being transported via radiation, whereas the deeper atmosphere is mainly convective, where convective mixing is driving the energy transport. Now, for any chemical reaction, for example, the conversion between methane and carbon monoxide, there's always a chemical timescale associated with that reaction. That is the time it takes for methane to go into CO or the other way around. But then since this is an atmosphere, you also have various mixing processes going on in the atmosphere due to convective mixing and things like that. And there's a mixing time scale associated with these processes. Now, if you look at this middle panel, this shows the red line shows you the chemical time scale for CO as a function of pressure in the atmosphere, whereas the green line shows you the mixing time scale in this atmosphere as a function of pressure. And if you look at this region in the deep atmosphere, the chemical time scale is much faster than the mixing. So what you get is equilibrium chemistry, because chemical reactions can complete before it is getting mixed. But when the two time scales intersect above that pressure, mixing is a much faster process. So you get basically quenched abundances, like as has been shown here. The deeper atmosphere is in chemical equilibrium, but above that quench point, you get quenched abundances. So this is what I mean by disequilibrium chemistry. Now, what we have done is that we have developed this 1D self-consistent radiative convective equilibrium model, which has a heritage from a Fortran code, which is often called EGP. And this model can take into account self-consistently this mixing and quenching process, and also model self-consistently the thermal structure, the chemistry, the radiative transfer, and the clouds all simultaneously, and give us a converged self-consistent profile. Now, this model will soon be made public as a part of Picasso. And the good thing is perhaps that this is all Python based. So it's perhaps a bit easier to use than Fortran models. Now, we have used this model to look at motivated by a certain set of observations done by Miles et al., who actually measured the amount of mixing in various brown dwarfs back in 2020. And this plot shows you the measured KZZ as a function of effective temperature of these brown dwarfs. And they saw that these brown dwarfs between 400 to 800 effective temperature have a very low amount of mixing compared to models which are shown, like models of convective quenching, which are shown by these dotted lines. So somehow in these brown dwarfs, mixing is very sluggish compared to much cooler brown dwarfs where it matches typical models. So we wanted to know why this is happening. And one of the hypotheses is that for some brown dwarfs, you can have two radiative zones. One, which is the conventional in the top of the atmosphere, but in some self-consistent models, it turns out another radiative zone is present, which is much deeper and is sandwiched between the convective zones. As you can intuitively think of it, that in the convective zones, there's a lot of mixing because there's a lot of convective mixing, and mixing timescales would be low. But in the radiative zone, you can expect the mixing timescales to be longer. So that if the quenching occurs in this intermediate radiative zone or the sandwich radiative zone, then if as an observer, if you measure the KZZ of this object, you would measure a much lower value than what is expected from convective zones. And then your abundances will be quenched at a lower pressure compared than if the quenching would have occurred in a convective zone. So if this happens, then you can expect to measure lower KZZs than convective zone KZZs, right? And but the question is that how, like, does this happen? This does not happen always. This radiative zone does not occur always. The question is at what temperatures does this radiative zone occurs? So we actually ran a grid of self-consistent models with this Python code. The grid is effective temperature versus the log G. And in this plot, I show you which of these models have this second radiative zone, and everything in bright here has a second radiative zone. So this is a good news that interestingly, between 400 to about 450 to 800 Kelvin, this second radiative zone occurs. So this is encouraging. Not only that, we also find that the mixing timescales in radiative zones is not well understood theoretically. We do not know the exact processes happening in these zones, and the mixing timescales are very uncertain, as opposed to convective zones where we use typically mixing length theory. Now, therefore we tried various very empirical formulas for, or empirical relations for the mixing timescales in the sandwiched radiative zones, and we found that the M-band spectrum of these brown dwarfs is really sensitive. But these brown dwarfs between 400 to 800 Kelvin and high gravity, their M-band spectrum is really sensitive to the mixing timescale we assume in the radiative zones. For example, here I show the M-band spectrum. This is a very low resolution M-band spectrum, but here I show you 3 M-band spectrum of the same brown dwarf, but with different mixing timescales in the radiative zone. So this is a good news, because with telescopes like James Webb, we will be able to measure the M-band spectrum of these colder T dwarfs. And as a result, we will be able to kind of have a estimate of the amount of mixing which can go on in a radiative zone, because that is not at all well understood. And this also kind of explains the observations done by Miles et al. And so just to summarize, we have developed this 1D radiative convective equilibrium model, which can do disequilibrium chemistry. And also, we have also tried it to couple it with chemical kinetics codes like Vulkan, so that can also be done. And we find that these brown dwarfs between 400 to 800 Kelvin, which are higher gravity, have like sandwiched radiative zones in the deep atmosphere. And the M-band spectrum of these brown dwarfs is sensitive to mixing timescales in the radiative zone. And JWST should be able to measure these timescales, and that would help us in better modeling the chemistry and clouds brown dwarfs overall. So thank you everyone for listening to me, and thank you for this amazing conference.
Thanks again, Sagnick. We are a little early on time, so there's plenty of time for questions. I guess I'll start off. I'm not super familiar with ground dwarf atmospheres, except to the extent that they're applied to exoplanets in some cases. But it looked in some of your plots that the mixing timescale was roughly constant in the convective zones across the pressure levels, but there was a smooth curve in the radiative zones. Can you explain that a little bit?
Yeah, for sure. Oops, sorry. Yeah, I think, yeah, in the convective zone, we are using like a physically motivated theory to calculate the mixing time scale, which is the mixing length theory. And that's why it's more or less like constant time scale throughout. But in the radiative zone, as I said, like we use an empirical relation. We have no clue what the mixing time scale there would be, but there are some empirical relations from Julian Moses' paper. And we are using that. And one of the reasons the mixing time scale is assumed to be smaller in the top atmosphere is because there are a lot of like gravity waves and things like that there, which can cause more mixing than the deeper parts. So that's the reason of that shape. Yeah.
Okay, thank you. And a question from Michael Lyon. Nice job. Can you comment on impacts for cooler transiting exoplanets, of which are top heated? Do you expect similar effects?
Yeah, that's a really great question. We haven't looked at exoplanets like irradiated cases yet, but I did a couple of simulations, and it looked like for irradiated exoplanets, the effect is smaller than brown dwarfs because there the irradiation dominates a lot of the temperature pressure profile. But yeah, I don't have an answer for that as of yet. But yeah, in future, we hope to look the exoplanets case as well and do all this for exoplanets as well.
Okay, any other audience questions? I guess I'll ask a follow-up then. Something that I think I was getting at in my earlier talk about retrievals, we only looked at free chemistry retrievals and didn't look at equilibrium chemistry because of the potential for big disequilibrium processes. Do you expect that this modeling could help actually disentangle some of that for observations in the near future?
Yeah, for sure. Yeah, this Python model can do like equilibrium chemistry, disequilibrium chemistry. You can also couple, like you can also kind of do photochemistry if you couple it with Vulkan. So this framework would be applicable to like irradiated exoplanets, brown dwarfs, even like if you want to do photochemistry. So yeah, I think so.
Cool. And with that, let's thank Sagnick again and move on to Louise Welbanks, who is also a NASA Sagan Fellow. but this time at Arizona State. And he'll be presenting a dissertation talk and towards generalized characterization of exoplanet atmospheres with transient spectroscopy. And since it's a dissertation talk, Luis, I'll give you a 5-minute warning and a 2-minute warning.
Fantastic. And let me ping, I will ping you so you can also just raise your hand in case I don't see the messages.
Okay.
Fantastic. Yeah, so thank you very much. My name is Luis Welbanks. I just landed in Arizona on Sunday, so I'm still getting used to everything. I'm a Sagan postdoctoral fellow here at ASU working with Mike Line. And I will talk to you about my dissertation talk, the work that I did as a PhD student at the University of Cambridge with Niku Madhusudan. And I want to give you an overview of the type of questions that were bothering me and that occupied my mind for the last 4 years, and that I want to discuss on this talk. First, we have already heard a lot about retrievals and different models that we can use and how these models can affect our inferences. So a key question would be, how can we obtain reliable inferences of these atmospheric properties, particularly for transiting exoplanets with current observations? Once we understand what do we need to do to get reliable inferences, can we use them? And can we use current observations so that we test our hypothesis of planet formation? With the plethora of observations that we have, what can we learn? And as we look towards the future, and well, not so distant future, thankfully now with James Webb, what are the considerations that our models and our retrieval frameworks must have so that we can be reliable in our interpretation of these hard to get observations? And as we move towards the generalized characterization of exoplanet atmospheres, I really care to find what are the limitations of current atmospheric models. Let's start first with a topic or a sentence that we've heard a lot in the last session, which is that the inferences derived from our observations are going to be strongly influenced by our model assumptions. Depending on the model assumptions, we're going to get different inferences. So these may mean, oh, we're doomed. This is a problem. If you use one model, you're going to get a different answer from mine. What is the true answer? Well, thinking about this as a problem, a way to perform or to offer a solution to this is to perform a systematic exploration of the degeneracies between different model considerations and the observations that can resolve them. That is, let's go through a gradient of model completeness where we also relax some of the assumptions in our models until we find what is the best that we can do with current observations and what is the bottom line that our models must consider to have reliable inferences for current observations. And that is part of what I did. Here I'm showing you 12 cases that go in increasing degrees of completeness, and I'm showing you the retrieved water abundance that each of these models obtains. I start with very simple semi-analytic, isobaric, isothermal models, and little by little, the assumptions of these models get relaxed. For example, removing the assumption of isobaric cross-sections, removing the assumption of isothermal atmospheres, including the presence of inhomogeneous clouds and hazes, and including more and more chemical species. And you can see that the median retrieved water abundances change, but also the error bars, the uncertainty in our inferences change, and those uncertainties change depending on which observations we expose our models to. But the key point here is that for current observations, there's a point where our solution converges to a particular retrieved inference. And importantly, not only is it that we can just see whether they converge or not to a particular answer, we can also test how these more complex models are preferred over the simpler semi-analytic isothermal isobaric models to find how these models are preferred and what is that we should be using. Not only can we look at them in the inference space, we can look at them in data space, where different models will provide some degree of fit to the observations in the optical. This is HD 219-458b, observations with HST, WC3, and STIS. But all of them provide a degree of fit to the HST, WC3 observations. But the observations in the optical, that's where we start actually discriminating. We start realizing which models perform better than the others. And to take an example, we see that, for instance, a model that does not have sodium and potassium in its assumptions fails to explain some absorption features that may be attributed to sodium and potassium. So it is important that our model has built in the features that are required for our observations. So with all of this in mind, how do we overcome the limitations with existing data? Well, our atmospheric inferences, our atmospheric retrievals must use physically motivated models. What does physically motivated models mean for current observations? Well, let's not assume isobaric cross-sections. Let's not assume isothermal atmospheres. Let's consider the possibility of inhomogeneous clouds and hazes. And in order to obtain reliable inferences, we must use high precision spectra in the optical and in the infrared. We need to also consider the latest and most reliable experimental and theoretical data. I'm talking here about cross-sections, because these cross-sections will have a strong impact in our inferences. And particularly when we're thinking about hot Jupiters, sodium and potassium are very important when we are looking into the interpretation of the observations in the optical, because this will help us get joint constraints on the properties of the clouds, the hazes, and other chemical abundances. So with this picture, we can then understand what is that we need to do to have reliable inferences with our current observations. So knowing our model and knowing our data, then we can begin to test our hypothesis on the primordial formation pathways of exoplanets. And we already heard from Megan that ultimately what we want to do is to look at the composition of an exoplanet and get hints of how a planet formed and where it formed. Particularly, the hypothesis that we're testing here is that the metallicity of the atmosphere increases with decreasing mass, which is a hallmark of core accretion and is a trend that we see in the solar system gas giant planets. And this is a focus of several previous studies, particularly the HST-WFC3 observations. They have tried to look at what is the water abundance on a series of exoplanets. They have tried to compare those retrieved abundances to the trend in the solar system. And these studies have also expanded to use the latest observations and a larger sample. Generally, these previous studies have found water abundances that are relatively lower than the solar system planet trend. So here you see, this is a work from Arasipin Haas, but also similar results were found by Joe Barstow in 2017, where the water abundances lie below the solar system trend. But there's a key problem with this, is that we don't know how to interpret these results. Is it that the low water abundances that we're getting are the result of low atmospheric metal content, or is it that there is an oxygen depletion? And with just one abundance for one chemical species, we cannot really distinguish this. So in order to resolve this, we really need to look at observations and constraints of more species beyond just water. And that is a second goal of my PhD, which is to determine the population level composition trends, leveraging all the data that we have, spanning optical and infrared, that we can cover observations from water and other key metallicity tracers such as sodium and potassium. So while previous efforts also limited their studies to hot Jupiters, we extended the sample to mini Neptunes so that we had a larger, more diverse sample, and we could leverage this population to scrutinize formation hypothesis. In total, we looked at 19 exoplanets with data in the optical and the infrared, spanning cool, temperate mini Neptunes with temperatures of 290 Kelvin, all the way to hotter, ultra hot Jupiters with equilibrium temperatures over 2700 Kelvin. From this study, we confirmed that 6 planets had strong detections of sodium, 6 planets had strong detections of potassium, and 14 had strong detections of water. These were confirmations of other studies. And I want to highlight to you the diversity in the water features. This is the sample that we have, and you see that not all water features look the same. The shapes and the strengths and the amplitudes of these features are very different, telling us that there is a diversity in the amount of water in these exoplanets. And a very similar picture can be seen when we looked at the sodium and potassium features. Some planets will have strong sodium features, but no potassium features. Some will have both, and some of them will have mutual features for all of them. But this is what is important, because this effort allows us to expand the analysis of the so-called mass metallicity trend to species beyond just water. So I want to put the results within the context of the solar system carbon abundances from methane. These are the observations that we have for the solar system. And this is a stellar value. All the results that I'm going to show you, I'm going to normalize them to their stellar abundances. So first, this is what we get when we looked at the sodium abundances. You see that we get very large error bars. Some of these observations do not allow us for tight constraints, but overall, the results suggest stellar or superstellar abundances based on sodium. And because of the large error bars, they're largely consistent with the solar system trend. A very similar picture we see with potassium, where the results are stellar or superstellar, and the large error bars allow us to say that it is consistent with the solar system trend. Some planets have a little bit tighter constraints than the others. And with water, we have a more diverse picture where for the gas giants, we have abundances that are generally stellar or substellar. Substellar, particularly for those planets with the best data and the tightest constraints. And for the low mass exoplanets on the Neptune range and the sub-Saturns, we have stellar or superstellar abundances. And we can do the same thing that we do with the solar system. We can try to fit a trend to these observations. And when we fit a trend, a linear trend to this is what we get. The general trend that we see is that we do see a trend of increasing metallicity with decreasing mass, but the overall trend is lower than that we see with the solar system. And this is what we get when we see all of them together. So this seems to indicate that water is all over the place. Many exoplanets have water, but it comes in smaller abundances than we were expecting. And these results are suggestive of stellar or superstellar metallicities, but a general depletion of oxygen compared to other species. And a key point is that we need to acknowledge that different chemical species provide different insights into the properties of exoplanet atmospheres. And with this approach, we can start breaking these intrinsic degeneracies in our interpretation of these results. And that way, it's also important to acknowledge that using retrievals where the metallicity is one of the parameters may be biased because different species can be differently enhanced. But still, we need more information, right? We need more planets to fit in this parameter space. It would be great to get more planets at lower masses and get more chemical species for this region of parameter space. So how do we do that? Well, fortunately for me and for all of us, we have the next generation of observations. And these next generation of observations promise to give us more observations of low mass exoplanets, which are intrinsically more diverse in their composition. And we will get observations from James Webb and Hubble and the ground-based facilities. So we need to start thinking, how do we bring together all these observations that will be higher fidelity and that will require more complex and flexible retrieval frameworks? So for that is that I started looking into developing next generation atmospheric retrieval studies, particularly Aurora. Aurora, the focus of this retrieval framework was to allow for a generalized compositional retrieval framework for hydrogen-rich and hydrogen-poor atmospheres that allows us to not assume that all exoplanets are hydrogen-rich, but also develop multidimensional frameworks that allow, for example, generalized prescriptions for inhomogeneous clouds and hazes, and to start looking into secondary effects that so far have been ignored, like refraction, forward scattering, and me-scattering. And one thing that I'm particularly interested too is on looking into different noise modeling functionalities, like underestimated variances, instrumental shifts, and also allowing to retrieve correlated noise in the data. Using a retrieval framework like this allows us to perform agnostic retrievals of mini-Neptunes where we no longer have to assume that it's hydrogen-rich. We can get a result from the data. We can let the data speak for itself and tell us what the abundance of hydrogen and helium is and how it affects other chemical species, secondary gases. We can look at this for hydrogen-poor atmosphere. This is simulated data for TRAPPIST-1D, where I've assumed a nitrogen-rich composition, but we could, in principle, retrieve the bulk composition of the atmosphere without making any a priori assumptions. And we can also fold those that lack of assumptions into the abundances of other gases like water, CO2, and even ozone. Here, we can retrieve the abundance of ozone, assuming that it is enhanced relative to Earth values. And by having this more flexible framework, we can also start building an increasing complexity in our inhomogeneous models built from the work from Line and Parmentier, where they propose that cloudy exoplanets can be analyzed as a superposition of clouds and clear atmospheric models to include clouds and hazes. And ultimately, what we've done here is to allow for different sectors that explain the observations with only hazes, with only clouds, with clouds and hazes, and clear atmospheres. So these efforts to start building multidimensional frameworks can also be expanded not only to clouds. We can, in principle, take the same idea from Line and Parmentier and take it from cloud inhomogeneities to terminator inhomogeneities and use linear superpositions to explore the combination of an evening and morning terminator or a day and night inhomogeneities. And using these multidimensional frameworks, we can start asking questions about how do our models perform? Particularly, for example, do we see that 1D models retrieve anomalously cold temperatures? And what we see from the sample of 19 exoplanets is that currently one-dimensional models do not retrieve anomalously cold temperatures, and the retrieved temperatures that we get are consistent with the expectations from the equilibrium temperature and the scheme temperature. And if we have a case where there are strong inhomogeneities, if we correctly implement these inhomogeneities, we can obtain reliable inferences even in the extreme cases. And more importantly, we can start learning what are the compositions and what are the parts of the exoplanet that are driving these inhomogeneities. We can start painting pictures about the information that is going on in the evening and morning of these exoplanets. So as a concluding statement, I want to highlight that in order to derive robust and reliable atmospheric properties, we must understand the limitations of our models. But just because our inferences will be affected by the model assumptions doesn't mean that everything is doomed. We can obtain chemical abundances that are robust when we use physically motivated models. And on the picture of mass metallicity trends, our initial picture seems to suggest that there are different formation pathways for the exoplanets that we've seen compared to the long period solar system giants. I am excited about the key developments that we will be implementing in future retrieval frameworks. And when it comes to the atmospheric retrievals with inhomogeneous terminators, I'm finding that overall the reported biases in atmospheric properties are the result of specific model assumptions and not necessarily intrinsic limitations in 1D models. However, there is a limit where we will get extreme terminator inhomogeneities. And when high quality data give us those observations, some of those inferences may be conceivably biased if we only use 1D models. And for that is that we've implemented a 2D retrieval framework and we're working on expanding this suite of models. Thank you very much. And thank you to the organizers for setting up this great seminar. Thank you.
Great talk, Luis. Thank you. It's very exciting work you've been doing. We have a question from Brad Hansen. A side effect of inhomogeneity is often time variability. Do you have any systems where you've observed at multiple times at different epochs and testing for variability in the quantities you infer?
Yeah, I agree. The one example that comes to mind is WASP 127, where it has been observed at different times with different instruments by different teams, and some of the data sets are not consistent with each other. So this is something that I am looking forward to exploring more in the future and building into this gradient of model complexity, time variability, and seeing whether the observations that we obtain can help us distinguish any time varying effects.
Okay, I'll jump in with a question of mine. A couple of slides ago, was it the WASP-12b? Yeah, WASP-12b doesn't look like it actually corresponded to the equilibrium and skin temperatures. Could you explain that a little bit?
Yeah, I invite you to also look at the paper. We have an explanation and a discussion on whether WASP-12b it is an outlier or not. By this means, it is an outlier. It is not consistent with the equilibrium temperature and the skin temperature, but starting to discuss whether the equilibrium temperature and the skin temperature are reasonable metrics for a hot Jupiter like WASP-12b. And looking at some GCM results, the photospheric temperature at the terminator can be significantly cooler than the equilibrium and skin temperature. So when we look at some GCM results for WASP-12, the photospheric temperature at the terminator can be consistent with our expected results. So it's thinking about how just using the equilibrium temperature as a metric does not in itself capture these inhomogeneities that we're searching. So let's use the right metrics for our exoplanets.
Cool. And a question from Ted Knocek. Very impressive thesis work. Can your Aurora framework constrain the different pressure levels at which clouds and hazes become optically thick in transmission on each limb from JWST quality data?
Yeah, so one of the key parameters in these treatments is the pressure level at which the cloud deck is. These are all parametric prescriptions. And one of the parameters is the cloud deck. So with James Webb-like data, we can start putting some constraints on the pressure level at which this cloud deck is present.
Any other audience questions? We still have plenty of time if people have questions. If not, we might be able to break about a minute early and handle any other questions online or offline. But otherwise, let's thank Luis and all of our speakers again for a really great session. And I believe we should be meeting back here at about 1:40 Eastern. So in 20 minutes.
Thank you, Yoni. Thank you, everyone.